Hello, everybody. I have good news. Two good news. One is that I was just accepted to Hogwarts, so here I am. I have my Harry Potter glasses. The other good news is that we're starting chapter 5. So let's do it right now. Now, if any of you ever took Calc 3, multivariable calculus, you're going to find that this is going to be very relevant to Calc 3. So you're going to know a lot of stuff in 5.1. That's what I'm trying to say. And if you had not taken Calc 3, then you're getting a head start with section 5.1. And we're going to start with vector length and unit vectors. So we mentioned the idea when we first introduced vectors in our class that vectors have magnitude and direction. Magnitude is a fancy word for length. And direction, of course, is direction. You know what direction means. The angle, whatever, you get the point. So so we're gonna learn about what does it mean, the length of a vector, and how do you figure out the length of a vector. And once we figure that out, we're gonna, let's take one step at a time. So the first thing is I got a vector right here. Right over here, there's a vector right there, nice little vector. So, and I know it goes up to I know the coordinates of where the vector goes up to. And I'm basically using the Pythagorean, so I know that it goes from the origin to the point v1 comma v2, and it looks like those are just real numbers. So I can figure out the length of this vector just using good old Pythagorean theorem, and which is what I'm about to do. And that's kind of similar, it's in what's the word I'm looking for? And when you do graphing, you use the distance formula, and the distance formula is really just Pythagorean theorem, basically. So this is usually what length means. Now the book says a very interesting mysterious line over here, and I'll tell you what it means, that this definition corresponds to the usual concept of length in Euclidean geometry. Now, why does it have to say that? Well, because we're going to use this same formula and apply it to 3 variables, 4 variables, 5 variables, 17 variables. In other words, even in spaces where length doesn't make that much of it doesn't even mean that much to us. Oh, the light is on now. Even in a place where vector length doesn't mean that much to us, we're going to still apply the same formula. That's kind of what we do. We're going to be doing a lot of. In other words, we're going to look at a formula that makes sense in like 2 dimensions or 3 dimensions, whatever, which we can picture, and we're going to apply that same formula to n dimensions, even though it may not have the same physical meaning, but we're going to still apply the formula, and it's still going to be very useful for us. That's what we do in math. We generalize things. Okay, so well, that light's bothering me. So let's so here's the definition of the length of a vector in Rn. So instead of saying we just had a 2-dimensional vector, so we had v1 squared plus v2 squared, period. If it's an n-dimensional vector, we're going to go say v1 squared plus v2 squared plus ... plus vn squared. Those ... is a very big thing in linear algebra, as you notice, and that is going to be what's called the length of the vector, and or sometimes they call it the norm of the vector. Personally, I find the word norm confusing, because sometimes we use the word normal to mean something else. What can you do? But this is the what can I say? Sometimes terms get confusing, but forget the terminology. Let's look at the math. So how do we find the length of a vector in R2? So we have a vector. We have a vector here, which is, let me just, I have to put my glasses on so I can see better. So we're in R5. Now R5, 5 dimensions. What does that even mean, 5 dimensions? You can't picture that, but don't worry about picturing it. It just means 5 variables. So we have a vector whose coordinates are 0, -2, 1, 4, -2. What is the length of this vector? Well, just plug it into the formula. It's the square root of 0 squared plus -2 squared plus 1 squared plus 4 squared plus -2 squared, and we are good to go. And of course, if you add all that up, that's 4 plus 1 plus 16 plus another 4. That adds up to 25. Square root of 25 is good old 5. 5 is not only the answer to this question, but it's also the dimension of the vector space, and it's the name of a gum, which is supposed to taste very good. Moving on. I think there was also a character in Peanuts named Five, if I recall. It's been a long time. Anyway, let's look at R3. Now, R3, that's something we can picture in regular space. That's three-dimensional space. So the length of the vector V, so we have a vector whose coordinates are 2 over rad 17, negative 2 over rad 17, and 3 over rad 17. And here we can actually picture it right there on the left side. And now this, by the way, I'm not proving this, but when you take Calc 3, you may prove this. This actually works physically, the Pythagorean theorem. And the reason is because to get from the origin to this point down there, that's the square root of x squared plus y squared. And then to get from, if you draw that little diagonal, which is missing, and then you have another triangle up in space. So if I square this, I get x squared plus y squared. If I square this, I get z squared. And now the square root of that is the square root of x squared plus y squared plus z squared. So this actually does make sense physically. It's not just an arbitrary extension. It does make sense physically in R3. So moving on, what is the length of this vector? So this becomes, let's see, 4 plus 4 plus 9, which is 17, over square root of 17 squared. So you get 17 over 17, which of course is a good old 1, square root of 1. Now, you may have noticed that in example 1b, the answer came out to be 1. When you have a vector whose magnitude, or in other words, that's another word for length, whose length is equal to 1, we call that a unit vector. That's it right there, a unit vector. So a unit vector is a vector whose magnitude is 1. And that's it. Anyway, now each vector in a standard basis of Rn has length 1, and that's called a standard unit. In other words, 1, 0, and 0, 1, 0, 0, 1. You notice that that's a 1. So the length of this vector is 1. Length of that. We've mentioned standard basis several times. We never pointed out that each vector in the standard that they have a length 1. So if you look at 1, 0, 0 has length 1, 0, 1, 0 has length 1, 0, 0, 1 has length 1. By the way, when you take Calc 3, you're going to, and often in a lot of areas of math, we refer to the vector 1, 0, we refer to it as the I vector, and 0, 1, we refer to that as the J vector. And when we go to R3, we call that the I vector, 0, 1, 0 is the J vector, and 0, 0, 1 is the K vector. It's just a name. It's just a commonly used name. And the I, that has nothing to do with the I that we know from imaginary numbers. There's nothing to, we're not talking about that I. We just mean the vector I. So when we talk about the vector I, and we may use that term, in our class. When we talk about the vector I, we're talking about, it was very eerie when you see the glasses and the reflection. When we talk about the vector I, we're talking about 1 followed by a bunch of zeros, depending on how many dimensions we're in. So the two now two vectors are parallel if they go, quote, in the same direction. What does same direction mean? It means if I multiply one vector times a scalar, I get the second vector. Now, when I multiply it by the scalar, I might make the vector longer. I might make it go in exactly the opposite direction, like a polar opposite direction. Polar, I don't mean polar like a polar bear, but I mean like 180-degree opposite direction. But nonetheless, we call those vectors parallel, just like parallel lines, because just like parallel lines are in the same direction, parallel lines, as you know from graphing, have the same slope, so on and so forth. We're using that terminology here with vectors. Now, this is important. Suppose V is a vector in Rn and C is a scalar. So then the magnitude of CV is C, or I should say the absolute value of C, times the magnitude of V. So in other words, when we multiply a vector times a scalar, we basically just, if we multiply a vector, for example, if we multiply a vector times 2, the magnitude doubles. If we multiply a vector times -3, the magnitude triples. You see what I'm saying? That's what this theorem is saying. It's really very easy to prove, because V was V1, V2, V1, V2 up to Vn, but CV is CV1, CV2, dot, 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 up to CVN. So the magnitude is going to be the magnitude of these components here, which means I'm squaring each of these components, which means I have a C squared and a C squared and a C squared, which is that's why it didn't matter if C was positive or negative because I'm squaring it. Now I could pull that out of the square root. See, because if I square it, I first I square them all, then I pull them all out, and then I have a C squared here. When I pull that C squared out of the square root, it becomes a plain C, or but positive. And this here by definition is the length of the original vector V, and Power theorem is proved. So that's what happens when you multiply a vector times a scalar, you get a vector that goes in the exact same direction. It might be precise negative, meaning like I'm saying precise opposite, like when you multiply, but the 180 degree. Now, because 180 degrees when you're in n-dimensional space may or may not have the same. But you get my point. I hope you do. By the way, this idea is going to be multiplying vectors by scalars. I don't want to give too much away, but it's going to be a big thing, and when we get to chapter 7. But I don't want to, we'll get there. Anyway, let's move on. So suppose you have a vector in Rn, and you want to create a unit vector which is in the same direction as the original vector. Well, all you got to do is take my original vector, divide it by its magnitude, and now I have a vector in the same direction with a magnitude of 1, and now I have a unit vector. And this is again very, very simple to prove. And so what are we saying? So we're saying that V, by the way, we're assuming the V is not a zero vector. Of course, zero vector is all bets are off. But if it's not a zero vector, and it should be here I believe it's here in the definition, it's not a zero vector. Where are we here? Yeah, V is a non-zero vector, because if it's a zero vector, there's really nothing to talk about. But if it's a non-zero vector, so that means the magnitude is not 0, and 1 over the magnitude is a positive number. It's not an undefined number. It's not 0. It's a positive number. So I could say that U is equal to 1 over magnitude V times vector V, and now the magnitude of U is going to be the magnitude of V over the magnitude of V. But this is just a constant which I could pull out of the magnitude, similar to the way I pull the scalar out. And we know that the magnitude of V is 1. That's the magnitude of V is whatever it is, divided by the magnitude of V, and then I get 1. I mean, there you go. So the process of finding a unit vector in the direction of V is called normalizing the vector V. That's just the name of that process. Alrighty. So let's find a unit vector that's in the direction of 3, -1, -2. So if I want to find basically take the vector, divide it by the magnitude, and that's going to be my answer. Very easy peasy lemon squeezy, very simple. So that's the vector 3, -1, 2. I don't have to do anything to that. I just have to take the magnitude, which using the formula 3 squared, -1 squared, plus 2 squared, square root of that whole thing, square root of 14. So my answer is just going to be, I could either write my answer this way, 3, -1, 2 times 1 over rad 14, or I could just put the rad 14 into the vector itself, and we're good to go. And that's it. That's our answer. Now here the book just checks it. If you square each thing, you wind up getting, 14 over 14, which is 1, and yes, so it is indeed. We're just checking that it is indeed a unit vector. Okay. Now that's going to be it for this video. We're going to make another video. I'm going to make a part 2. We're going to continue. Bye, everybody.